Hello everyone, this is a group presentation prepared by Team K for the subject BEKG 2443 Engineering Mathematics 2. These are our team members, which included me, Boey, Fong, Yeap, and Qian. Today we are here to discuss one of the four core concepts of the fundamental theorem of calculus, which is called Green's theorem. Green's theorem is a fundamental statement in the field of vector calculus. It reaches the concept of circulation and flux. This theorem relates a line integral around a simple closed curve C to a double integral over the planar region R that C encloses. This is the definition of Green's theorem. Let C be a positively oriented, piecewise moved, simple closed curve in the plane, and R is the region bounded by C. If two functions fxy and gxy for both have continuous first-order partial derivative on an open region that containing R, then we can apply the formula below. This formula representing the Green's theorem. If we want to find the area of the simple curve that has a line integral, we can rewrite the line integral as a double integral using the partial derivative of f and g function. We can see that the path of the curve is in counterclockwise direction.
Next, when the curve is run in clockwise direction, it means that it was a negatively oriented curve. The negative orientation will affect the calculation of Green's theorem by changing the sign of line integral as shown in the formula in the slide. The negatively oriented version of Green's theorem simply involves by adding a negative sign to the standard formula. This is because of the reverse direction of integration around the boundary curve. In this diagram, it shows that the region in a closed curve was break up into different boxes. There are vector fields that move around the boxes which are curved. While the curve from the neighbors may be cancel each other out, this means that there are only components which are tangent to the curve bounded the region. Hence, this can prove the formula of surface integral of the curve are equal to the path integral of the vector field that dotted in the tangential direction.
The previous concept we explained is about the circular form of Green's theorem. Now we move on to explain about the flux form of Green's theorem. It relates a double integral over region D to the flux across boundary C. You can see in the diagram, D is the region enclosed by C while N is the outward uninormal vector to the curve. So we can make it in the formula of line integral of F dot product N ds is equal to the double integral of region R divergence of F dA is also equal to double integral of partial derivative of f respect to x plus partial derivative of g respect to y dA. Okay, so let's move on to a simple example of flux form of Green's theorem. Let C be a circle of radius r centered at origin and let the vector field equal to xy. Calculate the flux across the C, and you can see the question is on the right. So in step 1, we let p equal to x and q equal to y. The partial derivative of p respect to x is 1, and the same goes to partial derivative of q respect to y is equal to 1. So we sub in the formula and we will get a double integral r 1 plus 1 dA. So we let it become dr d theta, which from r is from 0 to 2, while the theta is from 0 to 2 pi. So after we done some set of integration, we get a 8 pi in the solution. So this is the simulation using GeoGebra in this question of the flux form of Green's theorem, and you can have a look. So this is the simulation using GeoGebra. So let's move on to some simple application question of circular form of Green's theorem. So in first question, the question given is use Green's theorem to evaluate the integral c 3y minus e sine x dx plus 7x plus square root of y power 4 plus 1 dy, where c is the circle x squared plus y squared equal to 9. So we use GeoGebra to simulate the graph in below of this question. So in step 1, we let P equal to 3y minus e power sine x and Q equals to 7x plus square root of y power 4 plus 1, and the partial derivative of Q with respect to x is equal to 7 and the partial derivative of P with respect to y is equal to 3. By applying the theory and the formula which we given in the right, so we know that the derivative of C 3y minus e power sin x dx is plus 7x plus square root of y power 4 plus 1 dy is equal to double derivative of d 7 minus 3 dx dy. And we let it become dr d theta, which r is equal to 0 to 3 and theta is equal to 0 to 2 pi. And we do some integration method and we get the answer is 36 pi.
In this question, we are required to find the integral as shown inside the slide. Unlike the previous question, the graph was given. Therefore, we have to visualize the graph based on the information given from the question. From the word annulus and inequalities, we can identify that the graph to be a hollow circle with a radius of 2 and a radius of 1 hollow circle. As you can see, this is the graph we draw using the Desmos app. Although D is not simply connected, you can still use extended form of Green theorem to calculate the integral, since the integration occurs over an annulus. From the graph, we can see that we have two curves, which is x squared plus y squared equals to 1 and x squared plus y squared equals to 4. Let us assume that the path is an anti-clockwise direction, and we can convert it into a new parameter of x equals to r cos theta, or y equals to r sin theta, or x squared plus y squared equals to r squared. This parameter could make the integration easier to do. We are going to use Green theorem to calculate the integral instead of doing straight line integral. We're going to apply the methodology as shown in the slide before. Let us start. Double integral is the enclosed region is equals to partial g respect to x minus partial f respect to y, which f is the sine minus y cubed over 3 and g is y cubed over 3 plus sine x. After the differentiation, we got x squared plus y squared, which can then be converted to r squared. And don't forget, dA is equals to r dr d theta. For r, we integrate from 1 to 2, and the integration around the circle is from 0 to 2 pi. The result of line integral is 15 pi over 2. As you can see, it is more easier to use Green theorem than using the line integral, which we have to find the two line segments respectively. In this question, we are required to use the Green theorem to evaluate the integral, where c is shown below. Take note that for this graph, the direction of path is in clockwise direction. Therefore, we have to change the sign in the Green theorem. As I mentioned earlier, if the closed curve runs clockwise or in the negative orientation, then we should switch the sign. As you can see, the integral equation inside the white box, I've highlighted the sign, which means that I've changed the sign. So same method applies on this question 2, like we did in the question 1 and question 2. The only thing different in this question is that we don't need any parameters. So the result of the line integral for this question is 3500.
So let us see the importance of Green's theorem. Green's theorem allows for the conversion of difficult line integral into easier double integrals or vice versa. This is able to facilitate the calculation and providing the deeper insights into the nature of 2D fields.
Now, I would like to share about the application of Green's theorem. We use Green's theorem when we are given complex expression for the curve of complex line integrals. Green's theorem is extremely helpful in various fields of science and engineering by convert line integrals into double integrals, which can be easier to evaluate. Firstly, we can apply Green's theorem to calculate the amount of work done of the force acting on the particle moving along a closed curve. Next, Green's theorem also can act as the verification of conservativeness. For a vector field, if the integral around every closed curve is 0, then the field is conservative. Green's theorem can be used to verify this by checking if the curl of the vector field is 0 within a simply connected region. Green's theorem also used in fluid dynamics. It was applied to calculate the flux across the curve and water flow inside the curve. While in electromagnetism, Green's theorem can be used to relate electric field circulation around a closed loop to the electric charge within a loop. This is related to Gauss' law for the magnetism. In conclusion, Green's theorem is a powerful and adaptable tool in vector calculus that provides an important connection between the macroscopic and microscopic properties of a field. It bridges the concept of a line integral around a closed curve within a double integral over the region enclosed by the curve. This theorem not only simplifies the computation of complex integrals but also offers a deeper understanding of the behavior of vector fields. Green's theorem can be said as a stepping stone to more advanced theorems in mathematics, such as the generalized Stokes theorem, Gauss theorem, and it provides a deep insight into the divergence and curl operation in vector calculus. And these are the links that we use to find the information about Green's theorem to have a better understanding on this topic. And that's all for our presentation. Thank you.